Yeah, so hi
sharing?
everyone. I'm now a John Harvard fellow at Harvard, and I'm going to tell you, some interesting results we in the Hammer collaboration have obtained recently about luminous accretion disks, and with that I mean like high.
We don't see your slides yet.
Oh, that's strange because you're seeing my, no, I was not screen sharing.
Yes, please start screen sharing.
So I'm going to tell you some exciting results we recently obtained in the Hammer collaboration. As probably many of you are in this conference are aware, is black holes transition over the course of weeks, months, years to different accretion states. These different accretion states, they are known for many decades, and essentially at the moment we think they are primarily driven by the mass accretion rate fluctuations that come in very far from the accretion disk and then change things closer to the black hole. But also the magnetic field topology plays a role, I think. I will come back to that later. For example, usually black holes spend most of their time in the quiescent and the state which is on the right bottom. Then if the mass accretion rate increases, we typically see very strong jet. The spectrum still stays hard, but the luminosity increases a lot, and then slowly it seems like the jet shuts off, the spectrum becomes softer, and we enter this high soft state. And I'm going to talk a lot about this high soft state in this talk. And why are we really interested in these state transitions? Because I would say they don't only determine the disk luminosity and spectral hardness, but also the disk morphology. If you are dealing, for example, with a geometrically thick disk or a geometrically thin disk, and the radiative efficiency, the presence of jets is also closely tied to the accretion state. And then we come to another topic, that are the quasi-periodic oscillations, which also directly correlate with the accretion state. We know that they change frequency during state transitions, and we know also that certain QPOs exhibit certain behaviors, and that in certain states we see them and in other states we don't see them. So in my opinion, like understanding state transitions and understanding QPOs, it's kind of something similar, because if you, for example, have a model for a state transition that doesn't explain the shift in the QPO frequency, then this model is not like complete, because the two are so inherently tied. So you should have some kind of explanation in your theory. And these QPOs are also interesting in another way. That, I mean, it was already postulated a long time ago that multiple QPOs, if we understand their physical origin, that maybe they could say something about the black hole spin. When we talk about QPOs or state transitions, we need to be able to simulate accretion flows in all different states, from low to high luminosities. And what we essentially see, we see that most black holes, or at least most XRBs, spend most of their time in the low luminosity states, which is kind of captured by the simulations. But just this luminous states closer to the Eddington accretion rates are simply the simulations covering that challenging regime are very rare. Then in addition, we have the complexity that many accretion disks can be misaligned with the rotation axis of the black hole. And yes, with misaligned, there are arguments that many XRBs are aligned. But for example, in our solar system, the sun is misaligned by, I think, like 6 degrees with respect to to the orbits of the planets. And if you have a similar misalignment in an XRB, then you already, when you go into the luminous state, then already the misalignment angle is bigger than the thickness of the disk. So you will see tilt-related effects in the physics. And yeah, so that's also something that cannot be ignored. And yes, most simulations just assume that the spin and rotation axis of the black hole and disk are aligned with each other. And why is that? And why are there so few simulations of these luminous tilted disks? Just because it's very hard. These luminous disks are very thin, so you need a very high resolution and very small time step because of the high resolution, plus the viscous time of thin disks is very long. So you also need to run the simulations for a long time. This is compounded by the added complexity that we know in the high soft state, we don't see evidence for jets, which implies a toroidal magnetic field topology, because essentially all simulations, if you just put a poloidal magnetic field in a disk and this poloidal magnetic field gets vectored to a spinning black hole, you get a jet. And just resolving a toroidal magnetic field is just more complicated. All in all, like, yeah, I would say a thin luminous disk is at least 1,000, arguably like 10,000 times as expensive to simulate than just yeah, an accretion disk in the quiescent state. So what do we need to model accretion? We need magnetic fields. That's important because they drive they drive turbulence and launch the jets. Without the magnetic field, there would simply be barely any accretion and there would be no jets. We also need general relativity, especially for tilted systems. That's what you see in the right movie, precession. Because of the warping of space-time, an accretion disk might precess, so the rotation axis of the disk might spin around the spin axis of the black hole, which points along the z-axis in all of my movies that I'm going to show. Plus, yeah, for the luminous state, we need radiation because the disks are in certain parts radiation pressure supported, and the radiation cools the disk, which means that the disk becomes thin. And on top of that, we also need to take into account that when the density becomes low and the accretion time becomes short, that electrons and ions can firmly decouple, which again feeds back into the radiation because the electrons emit radiation and the ions don't. So if the ions cannot transfer their energy to the electrons, then the disk morphology will change. To make these simulations possible, like over the last, I think it's already 6-7 years, I've developed a new GRMHD code called Hammer. The present version solves the radiative to temperature GRMHD equations. Hammer makes use of various optimizations which make it highly efficient, including GPUs, which give a substantial speed up compared to CPU-based codes. In addition, Hammer has special features that make it especially suited to luminous accretion disks, like adaptive mesh refinement that allows it to focus resolution where it's needed, a local adaptive time step that evolves the grid, parts of the grid where the resolution is higher with a smaller time step, but part of the grid where the resolution is lower with a bigger time step, making the simulation cheaper and more accurate. Then we have like special grids, especially suited for tilted accretion disks that solve them with high accuracy and high efficiency. And this is all scalable to the biggest GPU clusters in the world. Now the Hammer collaboration has grown to multiple groups spanning Harvard, Amsterdam, Northwestern University, and Washington University, the Flatiron Institute, and many institutes, and really our goal, as actually from my side, really the goal is to understand, to improve our understanding of accretion in all accretion states, and not only focus on, let's say, the quiescent state of black holes, which is kind of typical in the GRMHD community. Then we want also to make observational predictions by ray tracing simulation data and benchmarking those predictions against real observational data to really put a stringent test on the theory and really start with basically the plain GRMHD equations and test those against real observations. The long-term vision would, of course, be a unified picture explaining the physics in all various accretion states and also the transition between accretion states and the relation of that to the QPOs we observe. The first simulation I want to show you was run like 2 years ago. It's a thin accretion disk tilted at 65 degrees. It has a toroidal magnetic field, so it would correspond to like an XRB in the high soft state. Yeah, the accretion disk seems thin, but it's very well resolved. It's better resolved than most GRMHD simulations, so we are really able to capture the turbulence and the dynamics with high accuracy. And also we ran it for a long time in GRMHD terms. I would say for a reasonable time for a thin accretion disk. That would be, I think, for a 10 solar mass black hole, this would be like 10 seconds. Yes, we start running, the accretion disk settles. And what you immediately see is that, yeah, the outer accretion disk kind of doesn't do anything. It just, rotates. But in the inner part of the accretion disk, like smaller accretion disks tear off and start processing, I think around like 45,000 Rg/c. Something interesting will happen. There we see actually the biggest tearing event. Yes, it happens now. We see the inner accretion disk tearing off and it starts precessing, which is very exciting because precession is one of, I think now the best model to explain low frequency quasi-periodic oscillations. Multiple of these tearing events are observed. They happen in cycles. So we start with no tearing, then a disk tears, precesses for maybe 5 periods, and then again reestablishes equilibrium. That's what you see now. There is no tearing, but I think again around like 115,000 Rg/c, you will see some a tearing event happening. Interestingly, contrary to what, for example, hydrodynamic simulations suggest, the disks that tear off are not really rings, but really like extended disks that are kept together through magnetic fields, just preventing them from disintegrating into too many rings. And very interestingly, also in these tilted accretion disks, I want to mention that in addition to accretion by the MRI turbulence, you also have lots of angular momentum cancellation. If you have one disk which is rotating in a different plane than the other disk, for example, the outer disk doesn't precess and then the inner disk precesses for 180 degrees, then angular momentum can cancel. And when this happens, the accretion speed can be ridiculously fast. Typically in observations, I think the alpha that's implied would be like 0.3. Most GRMHD simulations show much less than that, but in the case of disk tearing, we find like average accretion effective viscosities of like 3 to 10, which is just inconsistent with like the standard paradigm of accretion. Yes, then I want to I want to briefly summarize what we recently found out about QPOs in the collaboration. Jipva, who comes after me, will explain all of this much better in much more detail. But I mean, I've already shown that in this model, through disk tearing, it would be possible to generate low frequency QPOs, but also when we make power spectral densities, for example, in the left figure, you see a power spectral density before a tearing event, and in the right figure, you see it during a tearing event. We see a really strong radial epicyclic oscillation at the tearing radius of this accretion disk. And yes, it's not the Keplerian frequency, which is given in blue, but really the radial epicyclic frequency, which is in cyan, and neither is it the lens-fitting precession frequency, which is given in green. Yeah, so this is all very interesting, and Jipva will fill in all the details that I leave open for now. Yes, we are also working because these PSDs, they were just made by looking at the mass accretion rate. There is no like radiative transfer involved in this. So to test all of the conclusions, Andrew West at Washington University essentially read in the data from this hammer simulation and started making like really ray-traced light curve and spectra using extract. And the advantage of doing that compared to just looking at the data or making PSDs is that we can really look at the system from different viewing angles, and for example try to explain and see how the high frequency QPO, how the low frequency QPO really manifests itself from different inclinations, different viewing angles. And yeah, using that really try to get a more coherent and unified view of the appearance or non-appearance of various types of QPOs. Often, yeah, this is essentially the movie, and yeah, we see the tearing event, and we see indeed like stuff changing in the ray traced image. Plus there is this like, it's hard, I don't think you see my mouse, but there is like this oscillation that's visible.
We do see your mouse.
Yeah, okay, there is this oscillation, which is interesting in the sense of the high frequency QPO. And yes, often people ask me, what about jet precession? And yes, we also see jet precession in GRMHD simulations. This is another GRMHD simulation, which is very similar to the one I showed, only I started with a poloidal magnetic field. And a poloidal magnetic field, yeah, you put it on a black hole and then jet is launched, and this jet starts precessing. Because this jet is aligned with the rotation axis of the inner disk and not the black hole spin, because the inner disk also launches a wind which kind of torques the jet into the direction of its rotation axis, we see dramatic effects. We see this jet colliding with the outer disk, which leads to dissipation both in the disk and the jet, and that might be interesting in the sense, yeah, all for the dynamics, but it can also have interesting observational effects that I'm not going to talk about now, but it's worthwhile. I mean, you can ask me in Slack. Yeah, then in these simulations also provide a glimpse when QPOs might disappear. I mean, it has been postulated many decades ago that when you make a disk thin enough, that the rotation axis of the disk and the spin axis of a black hole can align together. But it was not really clear in simulations if this would really happen. And it happened in the hammer simulations. And here you see a video of this process where essentially the disk is cooled from a scale height of 0.03 to a scale height of 0.015, and during that process we see the alignment radius to move from 5 to 10 RG, which is much smaller than all the analytical models and the hydrodynamics simulations predict. And this Bardeen-Peterson alignment is important in the in kind of a unified picture of QPOs, because when you make a disk thin enough, for example, in the soft state, when the magnetic field is gone and the disk can really become thin, then if the alignment radius becomes bigger than the tearing radius, then a disk cannot tear and a disk cannot recess and the QPO will disappear.
5 minutes left.
Yes. In my last 5 minutes, I also want to show some of the latest results that we have from radiative simulations. All what you saw before that were like non-radiative GRMHD simulations where the cooling of the disk was just approximated by local cooling function, but we also performed radiative simulations. Yeah, I just started running. This is again a thin accretion disk with a poloidomagnetic field this time. And you see in this accretion disk like an inner very turbulent region, which is magnetic pressure supported, as I will show in the next slide. It's also a 2-temperature fluid. And it might be it might be the corona in reality. And in this model, like the corona is not a lamppost, it's clearly something with a strong outflowing component and also containing cool patches of gas. In this simulation, the truncation radius is at 20 RG, but the truncation radius will depend on the amount of magnetic flux in the disk. Yeah, we can plot the system with magnetic field lines given in black, and we see magnetic field lines going into the black hole, but also through the disk, which would be similar to this picture of this jet emitting disk. Yes, the inner accretion disk is magnetically arrested, which means that the magnetic pressure gradient exceeds the forces of gravity. And as gas essentially falls into the black hole through this like poloidomagnetic field, the electrons get heated to pretty high temperatures, like above 10 to the 8, and they emit in synchrotron. In addition, the ions get heated much more, 10 to the 10 Kelvin we find, but this doesn't include Compton cooling. The next generation of simulations will. So this is all preliminary, but it's really exciting that already the simulations that we can get like a 2-temperature truncated disk with a corona just with a normal just without doing anything like fancy, like including like including electron conduction or considering the effects of disk evaporation. So I had 2 bonus slides, but I'm already running over time, so I jump to the conclusions. Yeah, the recent simulations have shown that disk tearing and precession are important, that they can change the dynamics, they can change the appearance in terms of dynamics. The disk tearing really leads to much faster accretion than what you would expect based on normal GRMHD models. With this picture, with both having possibly this precession induced like low frequency QPO and finding this radial epicyclic oscillation, which might manifest itself pending future work as a high frequency QPO in the observations. I really think that that we might be getting close to explaining these QPOs. And also really exciting, that it's possible to get a truncated accretion disk where we essentially have this like hot and thick inner disk coupled to this cool and thin outer disk. And in the near future, we will probably know much more about this disk truncation and the formation and dynamics of this corona and the transition region. And then, yes, the next step will be combining both the best of the non-radiative models that I've shown, which is the tilt, and the radiative models, which were non-tilted, and really get to really simulate and understand what would happen to misaligned truncated accretion disks, and especially how the spectral hardness of the QPOs would evolve. Thank you all for your attention.
Thank you so much, Matthew. You were just like perfectly on time. Congratulations. Also amazing talk and amazing work. So questions, and I see questions
in the rooms too.
Yes, from Azaf first. Go ahead.
Yes. So thank you for a very nice talk. I have two questions for you.
Can you go? You do one question per person, please.
Most related. So the question is, we were mentioning that there is some efficient viscosity term that you get there, but you're solving the ideal MHD equations, aren't you? And
yes.
And the second question about the radiative term, you said that there is a cooling. Is it done by a sink term, or is it done in a different way?
So yes, I'm solving the ideal MHD equations with now also with radiation and two temperature dynamics, and the cooling, it's done by a combination. So it also includes the bound free terms, it includes Bremsstrahlung, but the synchrotron radiation is the most dominant in the corona. So it's not only done by synchrotron, there are also other terms like Bremsstrahlung, the molecular opacities and so on are all implemented, but synchrotron is the dominant opacity.
Is it done using the radiative stress energy tensor, or adding the sync term to the energy density in each cell?
It is just done. It is just frequency like gray opacities.
Okay.
Just with M1.
Thank you.
Yeah.
There are one of the questions from the in-person people. Go ahead.
Władek Kluźniak, hi Matthew, beautiful simulations. Would you mind showing the power spectrum again, the plot with the power spectrum?
Yeah, sure.
With the radial. So I'm
Yes.
not so much concerned about the future of simulations, but about past simulations. Would you care to? Right, so this plot is very reminiscent of a radiative simulation of a Kerr black hole accretion disk performed by Mishra et al. Some 3 years ago. This is published. And would you like to compare your result with that result? Because there's no tearing in that disk at all, and yet the same feature at about 12 gravitational radii appears.
I mean, this feature in our simulation really doesn't appear, let's say, when there is no tearing. That's on the left panel of this
Right,
video.
but I'm asking you to compare it not with your simulation, but with the published simulation of Mishra et al. 3 years ago.
Yes, I don't know exactly the origin of this feature in the Mishra et al. Simulation, but what I know is that, how would you say, that all the non-tilted models that they had, like, how would you say, that there was not like a very sharp radius, and here we see really like a very sharp peak that really follows this tear.
Perfect. Thank you. Would you mind pointing out the paper that you just mentioned on Slack? That would help. And the last question is from Zoom, Chris Reynolds. If you can do a quick question, that would be amazing.
Okay, relatively quick. So it's about resolution. I mean, the key piece of physics here is turbulence, and turbulence is multi-scale, tremendously multi-scale. So the fact that we have, you know, say a few dozen grid zones across your scale height is easy to believe it's not enough, and could affect fundamental things like whether the disk tears, for example. So how do you know that you're resolved?
So how do you know that? And that's really a good question. And I actually like the honest answer to that is how converged the results are, that you simply cannot say it at the moment, because to resolve such an accretion disk, the simulation is very expensive. Running it, of course, with like 64, 128, 256 cells per scale height would be just too expensive. But what we know is, for example, from the community-wide GRMHD code comparison, that we saw convergence starting at around 16 cells per scale height, and we are much above that. So I'm pretty confident that, let's say, the qualitative effects will be captured properly, but quantitatively, you know, if the strength of the turbulence changes, you know, maybe the tearing radius moves in a little bit out, but I'm pretty confident that really the effects that we see will still be there.